In Unit 3, we will discuss the idea of probability. So probability is very important in the field of statistics, especially when it comes to inferential statistics, because as we mentioned before, whenever we go to conduct inferential statistics, we need to control the error that comes from using a sample to estimate a population. So the way that we calculate and control that error is through probability. We calculate the probability of getting a certain error. So it's very important in order to understand inferential statistics that you understand this idea of probability. So we spend a whole unit just getting you comfortable with the idea of probability, and then we'll move into how we use probability in inferential statistics. So section A is really just an intro to probability, so some of the basics, some of the common things that you need to be able to calculate, the idea of what a sample space is, how we define probability in terms of an event, those kinds of basic ideas of how we set up probability. And then we'll really start to move into the idea of a probability distribution, which is what we really need for the application of inferential statistics. So let's start with an example, and we do lots of just basic examples in this section where we do things like roll dice and flip coins, and we'll also look at things in like a contingency table and calculate probabilities for the contingency table. So either we'll do simple experiments like rolling dice or flipping coins, or you'll be given the information that you need via a table in order to calculate the probabilities. So anytime you're dealing with an experiment and you want to calculate probability, the first thing you have to do is think about the outcomes. So in this case, we have a series of operations because we're doing basically two things. We're rolling a die and then we're flipping a coin. So we call those operations. So the first operation is that we roll a die. The second operation is that we flip a coin. So one of the first things we might want to know is how many possible outcomes are there. So this is a pretty simple counting principle problem. Really all you have to do is think about how many outcomes are there when you roll the die, and then how many outcomes are there when you flip the coin. And this is a multiplicative relationship. So when you have a series of operations, you just take how many outcomes there are for each one. And if you multiply those, that'll give you the total number of outcomes in your experiment. So here there are 12 possible outcomes, just 6 outcomes when you roll a die times 2 outcomes when you flip a coin, which gives you the 12 possible outcomes. When you're asked for the sample space is essentially a list of those outcomes. So in this case, we know there's 12 outcomes. So we want to list those outcomes out. So there's a few ways to do this. When you have a series of operations like we do here, one of the common things that we will use is a tree diagram. So a tree diagram is just a display that just gives you the possible outcomes in an experiment. So what you do with the tree diagram, you'll see the tree diagram in this case looks like this. What you do with the tree diagram is you start with the first operation. And here we know we have 6 possible outcomes when we roll the die. So you just start at a single point and you just create 6 branches. And then at the end of each of those branches, you want those to line up so it's nice and easy to read. Then you just list the possible outcomes. So the possible outcomes for that first operation, or the possible outcomes when you roll a die, are 1, 2, 3, 4, 5, and 6. So then off of each one of those, you want to look at your second operation. So notice if you get a 1, then we have 2 possible outcomes when we flip the coin. If we get a 2 on the die, then we also have 2 possible outcomes, and so on. So every time we get an outcome for the die, off of each one of those, we have 2 possible outcomes when we flip the coin. So basically you can see there, whenever we get a 1, we have 2 branches that extend from that. I just use H and T for heads and tails. Feel free to do that whenever you do this kind of work. You don't have to write out the word every time. Just use abbreviations. Lots of times, as long as the letters are different, you can just use the first letters as your abbreviations. That's what you will see me typically do. So you can see there we get 1. When we get a 1 on the die, we either get heads or tails on the coin. When we get a 2 on the die, we either get heads or tails on the coin, and so on. So this is the sample space. It's one way to identify the sample space when you have a series of operations. In terms of reading this, you can see the trailing branches. The trailing branches are basically the last set of branches for the last operation that you completed. So you can see the last operation here is flipping the coin. So if you actually count those, if you count that last column, you'll count that there are 12 possible outcomes here. And the way you read this is you start with that first outcome. That first outcome is basically 1H, and you just follow the branches and you get 1H. Your next outcome is 1T, then 2H, 2T. So this is just a list of those possible outcomes. So after you do this a while, you don't necessarily always have to create the tree diagram. You can actually just list out the outcomes, and this is how you would typically see the outcomes listed. So as you can see, of course, there are 12 possible outcomes here. And when you look at the outcomes and you see 1H, that means you got a 1 when you rolled the die, and you got heads when you flip the coin. So these are two of the ways that you can list out the outcomes. You can give a tree diagram, or you can just list them out. I highly recommend that you don't just list them out, especially as you start this stuff, because if you miss one or you put one in there twice, it's something that can happen when you just list them out. The tree diagram tends to take care of those issues. We do have one other way that we can display this information in terms of the sample space. We can also use a table. So here we have two operations. So if you want to use a table, in this case, it's pretty simple. You just let the rows of the table represent one operation, and the columns of the table represent the other operation. So I'm just going to let the columns represent the die and let the rows represent the coin. And when you do that, you will end up with a table that looks like this. So you can see the columns here are 1, 2, 3, 4, 5, or 6. Those are the outcomes when you roll the die. The rows are either heads or tails, and then within each cell of the table, you can see what the outcomes are. And those are the same outcomes as we got whenever we use the tree diagram. You get 1H, 1T, 2H, 2T, and so on. So those 12 outcomes within the table, those are the possible outcomes. Now with the table, if you have more than two operations, you only have two dimensions in the table. You only have the columns and the rows. So if you do have more than two operations, then you actually would have to combine those. You would actually have to combine some of those in order to put them in a table. For example, if you rolled a die and you flipped a coin twice, then you would have three operations, because you would roll a die, flip a coin, and then flip a coin. So what you'd have to do is you could set it up similar to this. You would let the columns of the table represent the outcomes when you roll the die, but you would have to let the rows of the table represent the outcomes when you flip the coin twice. So you're going to have to combine some of the operations if you have more than two operations and you're going to use a table. So sometimes the table is better, sometimes the tree diagram is better. It just kind of depends on the scenario. Lots of times whenever I ask you questions, I will actually tell you what to use. So if I tell you what to use, of course, that's what you should do. And the more you do this, the more you get a feel of kind of when each one is better. Okay, so that's your sample space. So once we get our outcomes, you have to have your outcomes, or at least you have to understand your outcomes before you can ever really even think about probability, because probability is based on the outcomes in the experiment. So whenever we go to define probability, we always define probability in terms of events. So I have the same table up here, but I also have two events identified. Events are typically denoted by just capital letters from our alphabet. So as you can see here, we have two events. One is A and the other one is B. And that's how we typically identify events. So A is defined as the die is a 5 or a 6. And I have that in blue. And you can see those two rows to the right. Those headings are also in blue, which identifies that is the outcomes that satisfy A. Is basically those last two columns within this table. The second event defined here is B, which is the coin is tails. The coin is tails, of course, is that bottom row in the table. So we have two events here. A is that the die is a 5 or a 6. B is that the coin is tails. And this is typically how we define events. So once we define events, then we can start calculating probabilities. So we're going to start with what we call the simple probabilities, and not necessarily because they're simple, but really because it's just the probability of an event. So whenever we take like the probability of A, we call that a simple probability. So the general idea of probability is basically the proportion of occurrences of A if you were to perform this experiment a large number of times. That's really what probability means. So the way that we calculate probability whenever we have all the possible outcomes is we basically take the number of outcomes in the event, and we divide that by the total number of outcomes. So we know our denominator here is going to be 12 because our denominator in most probabilities is however many outcomes we have in our sample space. So our denominator here is going to be 12. Our numerator for the probability of A is going to be, well, how many of those outcomes satisfy getting a 5 or a 6? And we're just going to base this on the table that we have up there at the top. And we can see those last two columns has 4 possible outcomes. So that means the probability of A is those 4 outcomes that satisfy A over the 12 possible outcomes in our sample space. That will give you 1/3 or 0.333. With probability, we typically write probability in terms of decimals. So that's what you should get used to. Give me 3 decimal places whenever you write probabilities. So you should write your probability, as you see here, 0.333. Probability of B is the same idea. B is that we get tails, right? And we know the probability that we get tails when we flip a coin is 1/2, because there's 1 outcome of tails out of the 2 possible outcomes. Here I'm going to do the same thing, but I am going to use the sample space to keep the denominator consistent. So the denominator is there are 12 possible outcomes in the sample space. That bottom row, those 6 outcomes satisfy getting tails. So that's just 6/12, which gives us what we would expect. We get a 50% or 0.5 chance of B occurring. So those are your simple probabilities. And we call them simple probabilities when we're just taking the probability of an event. The next one that we will calculate is called the complement. So the way we denote the complement is you always see a bar over top of the event. That'll tell you the complement of the event. The complement is a simple idea. The complement of A simply means everything not included in A. So if A is that the die is a 5 or a 6, then the complement of A is just that the die is not a 5 or a 6. So there's a couple ways to calculate this. One way is you can take all the possible outcomes that are not a 5 or a 6, so there are 8 of those, and you can take 8 divided by 12, and that will give you that probability. Another thing you can do, which is a really useful tool, is you can actually use what's called the complement rule, because we know that the total probability in any sample space has to be equal to 1. So if you take everything inside of A plus everything outside of A, and you take the probability of those and you add them together, you know that that total probability has to be 1 because it has to be the total probability in the sample space. It should make sense. Probability is 1, or if it was a percent, it would be 100%. You get 100% of the outcomes. That's how we think about probability. So one of the things we can do here to get the probability of A complement is we can simply just take 1 minus the probability of A, and that will give us the probability of A complement because we know those 2 things have to add to be equal to 1. So I will tell you that sometimes it is easier to calculate the complement of an event rather than calculate the event itself. So in those kinds of scenarios, what you can do is you can actually just calculate the complement, take 1 minus it, and you get the probability that you're interested in. Sometimes that is a useful option. So anyway, the probability of A complement, I use the complement rule here, which is just 1 minus the probability of A. That's 1 minus 4/12, which is 8/12. You can also get this from the table. There are 8 outcomes that are not in A. Out of the 12 outcomes, that will give you that 0.667 as a probability. The probability of B complement works the same way. The probability of B complement is going to just be 1 minus the probability of B. The complement of getting tails is getting heads. We know that is also 0.5 or 50%. So that one works the same way. So that is the idea of the complement. The next 2 probabilities are what we call joint probabilities. This is where we actually combine 2 events with either an and or with an or. So we'll start with the probability of A and B. So when you read the probability of A and B, it means exactly what it would mean when you read it. A and B means both A and B have occurred. So if you want the probability of A and B, that means you want the probability that the die is a 5 or a 6 and the coin is tails. So that's the way you read it. The probability of A and B means the probability of the die is a 5 or a 6 and the probability that the coin is tails. Both those things have to occur together. So basically the and is looking at the overlap. It's looking at the intersection or the overlap between these two events. So if you look at the table here, you'll see there's only two outcomes where both the die is a 5 or a 6 and the coin is tails. And those two outcomes are that 5t and that 6t. The bottom right corner is the overlap between that bottom row and those last two columns. So that means the probability of A and B is those two outcomes, that 5 tails and 6 tails. Those are the two outcomes that satisfy both. Out of the 12 possible outcomes in the sample space, that will give us that 0.167. The other joint probability is the OR, and it is the probability of A or B. The probability of A or B, again, is exactly like you read it. The probability of A or B would mean that the die is a 5 or a 6, or the coin is tails. So this means you need to include everything in both of these outcomes, but you have to be a little, or in both of these events, but you have to be a little careful here because you don't want to count the overlap twice. That's where sometimes people will make a mistake. So basically you have that bottom row, which is those 6 outcomes where the die is tails, and you have those last two columns where the die is either a 5 or a 6. So if you look at the overlap there, you have those two outcomes where 5t and 6t. So you can't just take 6 plus 4 because you're going to be counting those two outcomes in the overlap twice. So what you have to do is you have to, if you use the table, you can just take that bottom row, that's 6 outcomes, and then if you also add the two outcomes 5h and 6h, then of course you would get those 8 outcomes that satisfy the probability of A or B. The other way to do this is use what's called the addition rule, and this is actually what I recommend you do for the probability of A or B. The addition rule basically goes or uses the logic that I just talked about. You take everything in A plus everything in B, but you subtract out the overlap so you don't count that overlap twice. I recommend that you use the fractions when you go to calculate this so you don't get rounding error, because sometimes if you get rounding error, it'll throw off your answer by a little bit. So it's best to use the fractions when you plug into this equation. That's part of the reason why I like to use the common denominator of 12, because now we have this simple common denominator already. We don't have to deal with adding fractions other than just adding the numerators and putting it over 12. So we end up with the probability of A plus probability of B minus the overlap of probability of A and B. So in this case, that's 4 over 12 plus 6 over 12. And then we subtract out the 2 over 12. That gives us, as we mentioned earlier, that 8 over 12, which gives us a probability of A or B of 0.667. The next one is what we call a conditional probability, and I'll go ahead and show that one to you. This is the probability of A given B. So you'll see that vertical line there. We read that as a given. That's pretty typical notation in math. We write the probability of A, the vertical line is read as given, and then B, so we read that the probability of A given B. So you have a couple ways to do this one as well. So this is the scenario, this is the only one of these where the denominator is not the number of elements in the sample space. So the conditional probability, the condition changes your denominator. That's what the effect the condition has. It essentially changes what you're interested in. You're no longer interested in the whole sample space. Because if we read the probability of A given B, that means we are given that the coin is tails. So we know the coin is tails, so we don't even have to worry about that. So that means we're only looking at the bottom row of the table. We're only looking at those 6 outcomes where the coin is tails. We have those 6 outcomes where the coin is tails. Now, I would probably just use the table to do this, and I would say, well, I'm just looking at that bottom row, so my denominator is 6. And then I would say, out of those 6 elements, how many satisfy A? So we have these 2 elements where we have 5t and 6t that satisfy A within that bottom row. So that means our probability is 2 over 6, and you can see I have a probability of 2 over 6 there for that condition, which is 0.33. So one thing you can do is you can use the table. The other thing you can do with conditional probabilities, you can use the rule. The probability of A and B is always equal to the probability of A and B. divided by the probability of B. And this comes back to what I just said. Basically, the denominator of a conditional probability is how many elements are in the condition. So notice the condition here is B, which means you're only dealing with the outcomes that satisfy getting tails whenever you flip the coin. So that means your denominator becomes basically how many elements are in B, and that's where the denominator of this conditional probability rule comes from. The numerator is out of those elements in B, how many are also in A. So the numerator of a conditional probability is how many are in both. So you get the probability of A and B over the probability of B. That will always work for this conditional probability. If we plug those in, you'll see that you get basically 2 over 12 divided by 6 over 12, and the 12s are just going to cancel because the denominators here are going to be the same. So you just end up with 2 over 6, which gives you 0.333. So you can always use the rule as well. You can use the table or the rule for conditional probabilities. Do keep in mind that when we switch the order of these, the order does matter here. The order does not matter in the probability of A and B. If you write the probability of A and B, it's the same as writing the probability of B and A, because all that matters is it's the overlap. Same thing with the or. It doesn't matter if you write A or B, or if you write B or A. It doesn't matter the order. But with conditional probability, it does matter the order. The probability of A given B is different than the probability of B given A because your given or your condition is different. You really have to pay attention to what your condition is when you're calculating this. So if we rewrite this as the probability of B given A, the thing that changes is my denominator because my condition is now A. So when you use the rule, if you're going to use the rule, make sure that your denominator is whatever the condition is. So here the denominator would be the probability of A. So here we are given that the die is a 5 or a 6. So there are 4 outcomes where the die is a 5 or a 6. And then out of those 4 outcomes, 2 of those outcomes satisfy getting tails. That's 2 over 4, which is 0.5. You can also use the rule, take the probability of A and B, which is 2 over 12, divide by the probability of A here, because A is your condition. That's 4 over 12. You get 2 over 4, which is 0.5. So you can do that either way. So those are your 5 basic probabilities. You got to be able to calculate these. These are the simple probabilities, the complements, the ands, the ors, and then the conditions. Those are your 5 basic probabilities you have to be able to calculate. There are also a couple terms that are important here that I'm going to mention next. The first one is the idea of events being mutually exclusive. So here I just ask, are A and B mutually exclusive? Well, what mutually exclusive means is mutually exclusive is really a simple idea. A and B are mutually exclusive if they cannot happen at the same time. It's that simple. That's what mutually exclusive means. A and B are mutually exclusive if they cannot happen at the same time. Well, here, can the die be a 5 or a 6 and the coin be tails? Of course they can. They can both things can happen at the same time. For example, the outcome 5t satisfies both A and B. So the way that you do this mathematically is really simple. All you have to do is look at the probability of A and B, which we already calculated. That probability is 0.167. So we've already calculated that probability. The only way that events A and B are mutually exclusive is if this probability is 0. Because if the probability of A and B equals 0, that means it can never happen, meaning A and B can never happen at the same time. So if A and B are mutually exclusive, then this probability will be 0. Otherwise, if it's not 0, then the events can happen at the same time. So all you have to do to determine this is just look at this one probability. Look at the probability of A and B. If it's 0, then the events are mutually exclusive. If it is not 0, then they are not mutually exclusive. It's really that simple. There are other ones a little more messy, and this is an important one. We use this one a lot in statistics. It's the idea of independence. So the definition of independence technically is 2 events are independent if the occurrence or non-occurrence of one does not affect the probability of occurrence of the other. That's kind of the technical definition. But it's kind of hard to just grasp that whenever you throw out the definition there. So let's just think about it a little bit. In this case, it's quite obvious. But in most cases, I highly recommend that you check the mathematics of it to determine if 2 things are independent or dependent. So the general idea is here we're rolling a die and flipping a coin. So when we roll the die, is that going to have an effect on the outcome when we flip the coin? And of course, we know in this case it's not. Rolling a die and then flipping a coin, the outcome on the die is going to have absolutely no effect when you flip the coin. So that means these are going to be independent. But let's talk about how you check this mathematically. So to check this mathematically, you need to compare two probabilities. You need to compare the probability of A to the probability of A given B. If these two probabilities are equal, then that means events A and B are independent. If these two are not equal, then that means A and B are dependent. And the way this basically works is the probability of A and B means that given B has occurred, what's the probability of A? So if that is the same as just the probability of A, then that means the fact that B occurred did not have an effect on the probability, which means we've satisfied the definition of independence. B occurring did not change the probability of A, so that means B had no effect on it, which means these two events are independent. That's the way this works. But in terms of independence, all you have to do is compare these two probabilities. If they are equal, then that means they are independent. If they are not equal, then they are dependent. So here, yes, getting tails on the coin has no effect on the probability of getting a 5 or a 6 on the die. These are independent. And in this case, you can really just think about it. We know that what we get when we flip the coin is not going to affect what we get when we roll the die and vice versa. In most cases, though, it's a good idea to just verify by comparing these two probabilities, because there are some scenarios where I can make the numbers one thing and they're going to be independent, and I can make them something else and they're going to be dependent. So you want to make sure that you check the math on these, unless it's just an obvious case like rolling a die or flipping a coin. Okay, let's look at a different example. Now we're going to look at an example where you would just be given a table of information, and you would also be given what the events are defined as. And then we would go through basically the same process. So there are two common ways that you'll calculate probability in this section. You'll either have an experiment, something simple like rolling a die or flipping a coin, and you'll come up with the sample space. Or you'll be given information in a contingency table like this, where we look at frequencies of outcomes for a certain group. So here we have two variables. One variable identifies the individuals as either male or female, and the other variable identifies their political preference, Democrat, Republican, or Independent. And this is for a group of 36 people. So we define event A as being the individual is female, and we define event B as the individual being Democrat, and you can see the colors match up there as they did before. So green is female, and blue is Democrat. So green is event A, blue is event B. Okay, so it works the same way, only now we have these frequencies. Rather than having a list of outcomes, we have, we do have a list of outcomes from the sample, but it's formatted differently. It's not just a list of outcomes. Now it's the frequency at which, like that first cell represents there were 11 males that identified as Democrat. So we basically have frequencies within each of these cells rather than outcomes. But it works the same way. So the first thing we're going to do is find the probability of A. So A is that the individual is female. So there are, as you can see from the table, 16 females in this group out of 36 people total in the group. So the probability of A is simply just 16 over 36, which is 0.444. The probability of B, there were 18 people that identified as Democrat out of 36, which is 0.5. So that's the way this works. We're just using those frequencies within the table in order to calculate probability. And this is the second way that we commonly calculate probability. We base it on frequencies from a set of data. The complements, the probability of A complement is just going to be 1 minus 16 over 36. It's also going to be 20 over 36. You can see that from the table. So again, I don't care how you do this. There's actually lots of ways to do lots of these problems. I'm not real picky on how you do them, as long as you use a correct method in order to figure these out. So the probability of A complement, you can just take 1 minus probability of A. So that's 1 minus 16 over 36, which is 20 over 36, which is 0.556. Of course, you can also get the 20 out of 36 from the table itself. The probability of B complement, so there are 18 people that identified as Democrat. There are 18 people that did not, because 15 Republican and 3 independents gives us 18 that did not. We can also just take 1 minus that 0.5. We get 1 minus 18 over 36, which is also going to give us 0.5 here. So that is the complement of an event. The and. So the probability of A and B here means we're looking at people who satisfy both events. How many people were both female and identified as Democrat? And you can see that the overlap there from that female row and that Democrat column, there are 7 people that identified as both. So the probability of A and B is simply 7 over 36, which is 0.194. The probability of A or B, I would highly recommend that you just use the addition rule here. I think it makes it way easier than trying to use the table. You can get it from the table, but it is more messy from the table. For example, you can take, there were 16 females. There were also 11 people who were Democrat and male. If you add those together, then you'll get 27 over 36, which will give you the probability. But it's way, way easier to just use the rule, in my opinion. You take the probability of A plus probability of B minus the overlap probability of A or A and B, and that'll give you the total probability of A or B. So probability of A is 16 over 36, probability of B is 18 over 36, and the probability of A and B is 7 over 36, so you just take 16 plus 18 minus 7, gives you 27 over 36, and that will give you that probability of A or B, which is 0.75. The conditional probabilities, the probability of A given B, I would actually probably just use the table here, but you can use the table or use the rule. I'll show you the rule, but you can always just use the table. The probability of A given B means given that the individual is, identifies as Democrat, means there's 18 people that identify as a Democrat, that's your denominator. Out of those 18 people that identify as a Democrat, 7 identify as female, so that is 7 over 18, and that's going to be your probability. You can also use the rule. The probability of A given B is the probability of A and B over the probability of B. The probability of A and B, as we identified above, is 7 over 36. The probability of B is 18 over 36, so those 36s just cancel. That's the way these always work. The denominators are just going to cancel, and then you're left with 7 over 18, which is the same thing as I mentioned before. That will give you a probability of 0.389. So with these, you can either just use the table if you're comfortable using the table. You can also use the rule. If you're ever in doubt, it's good to use the rule because the rule will always work as long as you plug things in right. Probability of B given A. Well, the probability of B given A means, given A means you're given that they're female, so you're looking at only female, so the denominator here would be 16. Out of those 16 females, 7 identify as Democrat, so that's 7 over 16. That's one way to get the probability. The other way is to use the rule. Again, notice that our condition here is the probability of A. Our condition here is A, which means our denominator is the probability of A, I should say. That means this is probability of A and B, which is 7 over 36, divided by the probability of A, which is 16 over 36. That will give you 7 over 16, because again, those denominators of 36 just cancel. You're left with 7 over 16, which is 0.438. So once again, those are your probabilities. You're going to calculate those either through an experiment where you create a sample space, or a situation like this where you're given the outcomes from like a sample of 36 people like we have here, and you're calculating the probabilities based on frequencies. Let's look at our terms for this example. Are A and B mutually exclusive? And of course the answer to that is no. You can be both female and Democrat. So the probability of A and B is where you really look. That is not equal to 0. You can of course be both female and Democrat, so that means that these are not mutually exclusive. Are they independent? So this is one of those scenarios where it's best not to just think about the variables. Don't just think of does being female have an impact on whether or not someone might identify as a Democrat. It's best not to think about it like that, because if you don't look at the numbers, then you can make a mistake, because there might be one population where being female does have an effect. There might be another population where being a female does not have an effect. So you got to be careful there. And you got to make sure you look at the numbers. Basically what I'm saying is I can put the numbers in the table in such a way that these are going to be dependent, or I can put them in such a way that they're going to be independent. So you got to check the math here. So you got to compare, as we said before, you got to compare the probability of A to the probability of A given B. If these two are equal, then they're independent. If they are not equal, then they are at least somewhat dependent. So here, they are not equal. So no, here they are dependent. And like I mentioned before, it's important to look at the probabilities here, because it is not clear if being female impacts the probability of being Democrat without comparing these probabilities, because like I said, it might be true in one population and not true in another population. So you got to be really careful, and you got to make sure that you actually check the probabilities there. Okay, so those are your basic probabilities, your basic terms. We got one other thing to talk about in this section, and we've talked about all the rules except for one. We talked about the complement rule, we talked about the addition rule, we talked about the conditional probability rule. The last rule that we need to talk about is what's called the multiplication rule. So this last example will illustrate the multiplication rule, and it'll actually give us a chance to revisit one of the purposes of the complement rule. So here's our example. Suppose a box contains 3 red, 2 white, and 5 blue marbles. So there's a total of 10 marbles in this box. So we want to find the following. If you draw 3 marbles with replacement. So when you read these kind of problems, it's very important. This is common terminology that you'll see in these kinds of questions. Is you'll see these things say with replacement or without replacement. So they mean exactly what they say. If we say with replacement, it means once I draw the first marble, I'm going to put it back in, and then I'm going to, once they're shook up or whatever, I'm going to draw the second marble, and then I'm going to put it back in. So you're replacing it every time you draw a marble out. If it says without replacement, it means that once I draw the marble, I'm not going to put it back in. I'm just going to go ahead and draw the second marble. So that's really what we mean by with replacement and without replacement. It's important to note whenever you're looking at these kinds of problems. So if you draw 3 marbles with replacement, what is the probability that all 3 are blue? So this is an application of the multiplication rule. So when you're doing a series of things and you want the probability that they all occur. So here we're doing a series of things. We're drawing 3 marbles, and we want the probability that all 3 are blue. So basically what you do with the multiplication rule is you take the operations individually, and you say, okay, I'm drawing the first marble. What's the probability that it's blue? Well, we know there's 5 blue marbles, and there's 10 total marbles, so the probability the first marble is blue is 5 over 10. And then we say, well, what about the second marble? Well, here we're replacing the marble once we draw it. So the probability the second marble is blue is also 5 over 10. And then since we're replacing it, the probability the third marble is blue is also 5 over 10. So the multiplication rule says we basically take 5 over 10, which is the probability for the first marble, times 5 over 10, the probability for the second marble, times 5 over 10, the probability for the third marble being blue, and that will give us the total probability. So this is how the multiplication rule works. You look at the probability for each operation. If you multiply those together, it gives you the probability that they all occur. So when you read this, it says 5 over 10, that's the probability the first marble is blue, times 5 over 10, that's the probability the second marble is blue, times 5 over 10, that's the probability the third marble is blue. So we multiply that across, we get 125 over 1,000. That gives us a probability of 0.125. Let's do this same thing, but let's do it without replacement. So when you do it without replacement, it's a little different, because once you draw the first marble, you're not going to put it back in. So when you draw the first marble, the probability of getting a blue is still 5 over 10. But the deal is, is when that first marble is a blue marble and you don't put it back in, then you're going to change the probability that the second marble is blue. So if the probability the first marble is blue is 5/10 and you take a blue one out, the probability the second marble is blue, now you have one less marble in there, so there's only 9 marbles. Only 4 of those are now blue because you've taken one out. So the probability the next marble is blue is 4/9. So you get 5/10 for the probability the first one is blue, 4/9 for the probability the second marble is blue because you've taken a blue one out. And then when you get to the third draw, now you've taken 2 blue marbles out, which means you only have 8 marbles left, 3 of which are blue. So the probability the third one is blue is 3/8. So again, you multiply across, you get 5 times 4 times 3 is 60, 10 times 9 times 8, 720. Divide that out, you get a probability of all 3 being blue of 0.083. So this is how the multiplication rule works. You can see the difference between situations where it's with replacement and without replacement. Here's another important kind of problem that you need to be able to look at. So this is very similar to the previous one, but there's a big difference here as well. It says if we draw 3 marbles without replacement. So it's very similar to the previous one where we're doing this without replacement. We want, what is the probability that at least one of the marbles are not blue? So you want at least one not being blue. So this is one of those scenarios where you could calculate it directly. However, if you calculate it directly, it's going to be kind of messy because if you're looking at least one is not blue, well, it could be the first one that is not blue, or it could be the second one is not blue, or it could be the third one is not blue. Or it could be the first 2 is not blue, or the last 2, or the first and last. Or it could be all 3 are not blue. Any of those would satisfy at least one not being blue. So if you're going to calculate this directly, you would have to calculate all those different probabilities. And then from those different probabilities, if you add them all together, you would get the probability that at least one is not blue. So that would take a while, and that's not the best way to do this problem. When you read things and you read probabilities and it says things like at least one of the best things and most important things to think about is when it says at least one or at least something, it's always good to think about how to calculate the probability directly, as I just mentioned. And it's also important to think about how would I calculate the complement of this probability? What is the complement of at least one of the marbles not being blue? Well, the complement of at least one not being blue is that they're all blue. So since the complement of this is that they're all blue, we just calculated that probability. That probability is 0.083. So we know the complement of what we're interested in here is 0.083. That means I can just use the complement rule and just take 1 minus 0.083 and I get 0.917 for this probability. Sometimes the complement of an event is easier to calculate than the event itself. And when you're in that scenario, all you have to do is calculate the complement. Notice the complement here is only calculating one probability. We just calculate the probability that all 3 are blue. If we tried to calculate the probability that at least one is not blue directly, we would have a bunch of different probabilities to calculate, and then we would have to add all those together. But the easier way to do this is to just simply take the complement of that one probability, the probability that all 3 are blue. So when you read things like at least one or something like that, when you read those kinds of probability questions, the thing that you should always think about is is the complement easier to calculate than the probability itself? Because if that's the case, all you have to do is calculate the complement, subtract it from 1 by the complement rule, and that will give you the probability that you're interested in. And that is the way to do these kinds of problems. So this is really an application of the multiplication rule and the complement rule. With these kinds of questions, those are the 2 rules you commonly use. So in this section, you got to know the 5 basic probabilities, simple probabilities, complements, ands, ors, conditions. You got to be able to calculate those. You got to be able to identify things as mutually exclusive, independent, know the difference between independence and dependence, know how to answer questions like, are these events independent? You have to know your rules. You should know, you don't have to memorize them, but you have to be able to use them. You should be able to use the complement rule, the addition rule, the conditional probability rule, and then the multiplication rule. Those are your rules. So that's the focus of this section, just getting you comfortable with the idea of probability, which is what we're going to talk about in this unit. So that is the end of section 3A.